I think audio video clear hai bhai. Okay, so in today's topic we'll discuss with sinusoidal PWM, because sinusoidal PWM is most important topic. And if you look at the recent year, like last year or last to last year, almost every year they ask question from sinusoidal PWM. So this is again very interesting topic and very important. So I hope you will enjoy this session, and I hope you will understand what is sinusoidal PWM. Okay, so let's start the session, guys. This is my introduction, and I'll teach almost every subject. So the next subject will be electrical machines. First, I'll take some questions on different chapters like synchronous machine and induction machine, and then I'll switch the subject. Okay, so the next subject is synchronous machine. Before going to the lecture, or maybe before starting, you can subscribe this channel and like this session and press the bell icon so that you get the notifications. Okay, so जो ये सीरीज चल रही है, दिस सीरीज इज गेट एमर सीरीज, और इस सीरीज में हम लोग कंसेप्ट पे फोकस कर रहे हैं. जो इंपॉर्टेंट कंसेप्ट्स हैं उनको हम लोग डिलीवर कर रहे हैं. देयर आर सम अदर सीरीज ऑल्सो, उनका भी आप फायदा उठा सकते हो. बट उससे पहले अगर आपका कोई जूनियर है और मे बी कोई अगर, तो हमारे वर्कशॉप चलते रहते हैं. लाइक 20th को भी हमारा वर्कशॉप हुआ था, तो ऐसे ही वर्कशॉप और भी आगे आएंगे, तो आप वो वर्कशॉप भी ज्वाइन कर सकते हो. नीचे लिंक हमारा दिया होता है रजिस्ट्रेशन के लिए, तो आप वहां पे रजिस्टर करके वर्कशॉप भी ज्वाइन कर सकते हो दोस्तों. देयर इज वन मोर सीरीज विच इज गोइंग ऑन, दैट इज गेट PYQ सीरीज. इन दिस सीरीज हम लास्ट 5 years के जो PYQs हैं उनको हम सोल्व करवा रहे हैं. तो मेक श्योर कि आप ये सीरीज भी जरूर ज्वाइन करें, आपको काफी फायदा होगा इस सीरीज से भी. तो इस सीरीज का मैं जो ले रहा हूँ वो पावर इलेक्ट्रॉनिक्स ले रहा हूँ. तो पावर इलेक्ट्रॉनिक्स मैंने लास्ट लिया था सेशन, आपने देखा भी होगा. तो आपने अगर नहीं देखा है तो उस सेशन को यू कैन वॉच इट, इट्स इन द रिकॉर्डेड फॉर्म, सो यू कैन वॉच दैट. तो लास्ट 5 years के हमें क्वेश्चंस लेने हैं उसमें. बट in the previous session, in my session in power electronics, I have to take one more session on power electronics, because in the last session I have covered only 15 questions. And I need to cover approximately 26 questions. So almost 10 questions are there that I need to discuss. So I'll discuss those questions in the next session. Okay. So let me tell you guys, अभी जो टाइम है वो टेस्ट सीरीज का टाइम है. टेस्ट सीरीज बहुत इंपॉर्टेंट है और आपको अभी टेस्ट सीरीज स्टार्ट कर देना चाहिए, बिकॉज टेस्ट सीरीज से ही आपको पता चलेगा कि आप किस तरह की मिस्टेक्स कर रहे हो, कहाँ पे क्या गलतियां हो रही हैं, उन गलतियों को कैसे रेक्टिफाई करना है. ये सारी चीजें जो है वो टेस्ट सीरीज आपको बताएगी. नाउ यू कैन ज्वाइन दिस टेस्ट सीरीज एंड स्टार्ट गिविंग द टेस्ट्स. ओके, बायजूस एग्जाम प्रेप भी आपको टेस्ट सीरीज प्रोवाइड कर रहा है. सो मेक श्योर कि आप वो टेस्ट सीरीज ज्वाइन करें. एंड बिल्कुल कॉस्टली नहीं है, बिल्कुल आप मतलब कम प्राइस में अवेलेबल है. ऑलमोस्ट 60+ टेस्ट है, मतलब 60 से ज़्यादा ही होंगे. और फुल सब्जेक्ट टेस्ट भी है, फुल सिलेबस टेस्ट भी है, मतलब मॉक टेस्ट जिनको आप बोलते हो, तो वो सब भी है. तो उनका भी आप फायदा उठाइए. बिल्कुल जो इंटरफेस IIT का होता है एग्जैक्टली सेम इंटरफेस के साथ आपको प्रोवाइड किया जा रहा है. सो मेक श्योर कि आप इसको अटेंड करें. ओके, सो लेट्स स्टार्ट द सेशन गाइस. बट मैं बता दूं कि ऑल इंडिया ओपन मॉक टेस्ट है, उसके लिए आप रजिस्टर कर सकते हो. नीचे लिंक दिया हुआ है, वहां से आप रजिस्टर कर सकते हो. ठीक है, चलिए तो स्टार्ट करते हैं दोस्तों. एंड आज का जो हमारा टॉपिक है वो है साइनसोइडल PWM. हम इसको क्यों पढ़ें, साइनसोइडल PWM को क्यों हम देखें, जरूरत क्या है साइनसोइडल PWM की. बिकॉज द प्रॉब्लम इज वी वांट साइन वेव एट द आउटपुट. द प्रॉब्लम इज, जरा देखिए, द प्रॉब्लम इज लेट्स से आई हैव a single phase voltage source inverter. Let's say I have this voltage source inverter. This is the voltage source inverter I have. Now if you look at the output voltage, let's say this is VDC, and here I have connected 2 capacitors, and let's say this middle point is grounded. So with respect to ground, if you look at the upper point and the lower point, now you can see that this VDC is the total voltage across these 2 capacitors, and these 2 capacitors are equal value. So if the capacitors are equal value, then the upper point will be VDC by 2, and this capacitor is also charged at VDC by 2. Now with respect to ground, the upper point will be at VDC by 2 and the lower point will be at minus VDC by 2. You can see that. Since there are two capacitors and the capacitors have same value, so if the capacitors have same value, then this VDC can be divided into two parts, like VDC by 2 here and VDC by 2 here. With respect to ground, the upper point will be VDC by 2 and the lower point will be minus VDC by 2. Okay. Now we have this leg, we call it leg A. Let's call it A point and let's call it B point. So this is SA plus and this is SA minus. Similarly, we have SB plus and SB minus. Now we have two legs, A and B. In each leg we have two switches, SA plus and SA minus. Similarly, SB plus and SB minus. Now let's say I'm turning on SA plus and SB minus, and then I turn it off. I turn off both the switches, and then I turn on SB plus and SA minus again. Alternatively, I do like this. So the output voltage, or you can say the voltage at this point and at this point, you can plot that voltage. Let me plot for you. So VAO, first of all, let's look at VAO. So VAO will be, if SA plus is on, let's say 0 to T by 2, this point is T by 2, we call it T by 2. From 0 to T by 2, SA plus and SB minus is on. So if SA plus and SB minus is on, 0 to T on, 0 to T by 2 rather, 0 to T by 2. Now you can say that here SA plus is on, here SB minus is on. So this point will be connected at this point. This point is connected with this point, and the voltage at this point will be VDC by 2 with respect to ground, obviously, because this point is O. So with respect to ground, the point A has the voltage VDC by 2. So you can plot it here, VDC by 2. This is VDC by 2. Okay. Now from T by 2, from 0 to T by 2, this SB minus is also on. If SB minus is on, then this point voltage with respect to O is minus VDC by 2. So you can say that this voltage is minus VDC by 2. Okay. Now from T by 2 to T by 2 to T, let's look at the voltage from T by 2 to T. From T by 2 to T, you can see that this is off, this is off, this is on, and this is on. SB plus and SA minus is on. It means I have made the grouping now. SA plus and SB minus. This is group 1 and SB plus and SA minus. This is group number 2. So now SA plus and SB minus are off, and I have switched on SB plus and SA minus. These two switches are on now. If they are on, then the voltage at this point with respect to ground is minus VDC by 2, because this point is connected with the lower point. So you can say that the VAO will be minus VDC by 2. Okay. And here VBO, in VBO, since you know that SB plus is on, so this point is connected with plus VDC by 2. So you can say that this point is connected with plus VDC by 2. Plus VDC by 2. Okay. So this way you can plot the wave shape for VAO and VBO. Now the question is, what is the output voltage? What is the output voltage? Output voltage is this volt, VA minus VB. So we need to plot VAB. VAB will be the output voltage. So now let's plot the output voltage. So the output voltage is VAB. And VAB will look like from 0 to T by 2, VAO minus VBO. VAO minus VBO I have to apply. Now VAO is plus VDC by 2 and VBO is minus VDC by 2. So if you subtract them, because VAB is VAO minus VBO, no? So if you subtract them, it is plus VDC by 2 minus or minus VDC by 2. So it will become plus VDC. It will become plus VDC. From T by 2 to T, VAO is minus VDC by 2 and VBO is plus VDC by 2. If you subtract minus VDC by 2 minus of this VDC by 2, you'll get minus VDC. I hope you understood it. So this will be my output voltage. You can see that. This will be my output voltage. Now you can see that the output voltage is a square wave. Output voltage is a square wave. And in this square wave, we have harmonics. If you use the Fourier analysis, if you apply the Fourier, if you ask the Fourier, then the output voltage V naught T is equal to VABT, and that is equal to sum of 4 into VDC by N pi sine of N omega naught T. N from 1 to infinity, and N is odd. So it contains odd harmonics. It contains odd harmonics sine terms. Because the signal is odd and it contains odd harmonics, that's why if you apply the Fourier analysis, the Fourier, if you break this signal, then these terms will be present. If you can open it, you can put the value of N should be odd starting with 1. Okay, so V naught T will be equal to, if you open this summation and you put N equal to 1, you'll get 4 VDC by pi sine of omega naught T, and then N equal to 3. At N equal to 3, it will be 4 VDC upon 3 pi sine of 3 omega naught T. Okay, so you can say that there are odd harmonics. Now we don't want harmonics because these harmonics are problematic for us. We want to eliminate these harmonics. We want pure sine wave at the output. Now it's difficult to achieve pure sine wave here. It's difficult to achieve pure sine wave. Why? Because the harmonics are there, na? The odd harmonics are there. If odd harmonics are there, then you have to eliminate these odd harmonics, and it's difficult to eliminate them. You need a filter, okay? And using the filter, it's difficult to eliminate the lower order harmonic like 3rd and 5th and 7th. You can eliminate higher order harmonic, no problem. Higher order harmonic can be eliminated using filter, because for higher frequency, the component required, L and C are required, are very, we require low value of C and L to eliminate higher harmonics. But to eliminate lower harmonics, the filter will become bulky. You need L, very high value of L, okay? Similarly, C should be of very high value. So that's the problem. That's why what we want to do is we want to eliminate these harmonics so that we get the pure sine wave, so that it can be pure sine wave inverter. Now this is the problem, guys. So how to tackle this problem? How to tackle this problem? This problem can be tackled using harmonic elimination. So let's try to do harmonic elimination, and the best way to eliminate the harmonic is by switching, okay? If we can switch these switches are switched such that we get such that this third harmonic can be eliminated by itself, then there is no need to remove it. So using the switching, we can eliminate the harmonics. Using the switching, we can eliminate the harmonics. Now how to do that switching? How to do this kind of switching so that this third harmonic or fifth harmonic can be eliminated? Okay, let's try to do that. So what we want to do is we want to do some kind of switching. Now let's do the switching process. I have this inverter. I have this voltage source inverter. You can see that this is the voltage source inverter I have, and in this voltage source inverter, again here I have VDC, this is VDC, and I have connected two capacitors like this, okay, and this is grounded. This is SA plus and this is SA minus, SB plus and SB minus. This point is A and this point is B. Okay. Now what I want to do is I want to do some kind of switching. Let's do the switching so that this output voltage can be changed. Okay. What I did is, let's call it omega t axis. Let's call it omega t axis. At the half period, you write t by 2. But whenever the axis is omega t, you write pi. Okay, so this instant is pi. Half period is called pi radian. Full period we call 2 pi radian. Okay. Now I want to plot V naught t. I want to plot V naught t. How to plot V naught t such that we can eliminate some harmonics. To eliminate harmonics, what I need to do is I need to do some kind of switching. So let's do the switching. Let's do the switching. So what I did is first I turned on S1, SA plus and SB minus. I turned on these two switches. If you turn on these two switches, then the output voltage will be VDC. Output voltage will be VDC. Now, you turn it off at some angle alpha. What you did is you turn them off and you turn them on. Like SB plus and SA minus is turned on. It means you are not waiting up to half period. You are not turning SA plus and SB minus up to half period. Before that, before coming to this pi point, you turn them off and turn them on. SB plus and SA minus. You are going to turn them on. Okay. So if you are going to turn them on, then the output voltage will be minus VDC. Output voltage will be minus VDC up to pi, let's say. Now, at pi, rather, wait a minute. Let me change the process, or maybe wait a minute. Let me tell you from the initial point. This is pi by 2. This is 1/4. Okay. Now what I did is I turned SA plus and SB minus. So the output voltage is VDC by 2, or output voltage is VDC because this point is connected here and this point is connected here. So you can say that the output voltage is VDC up to alpha. This point is alpha, let's say. This point is alpha. So up to alpha, output voltage is VDC. Okay, output voltage is VDC. Now, from alpha to pi by 2, what I did is I turned them off and turned them on, SB plus and SA minus. So the output voltage will be minus VDC up to pi by 2. This is 1/4. This is half period. This is the quarter period. So you can say in 1/4 I did one switching. Now what I'm going to do is next SB plus and SA minus will keep, I'll keep them on. Okay. Don't make them off at pi by 2. No. They should keep conducting. Okay. So they are keep conducting. And then at this point at pi minus alpha, what I did is I switched them off. SB plus and SA minus, and then again SA plus and SB minus. Okay. This point is pi by alpha, pi minus alpha. Okay. So this is again pi. So I switched like this. Now, after pi, this wave should, I switch them such that the wave is inverted. It means after pi, what you can do is, you can make it like this. This is, now the same wave you can invert it. 0 to pi, whatever the wave is, you can invert it. So this wave will invert it, and this starting point will go here, and then it will go like this. This will be pi plus alpha, and then it will remain like this. Okay. So I switched it like this. Now it's very difficult to understand it. It's very difficult to understand it. What is the simple way to analyze it? The simple way to analyze it is that, take 1/4. Take 1/4 and do one switching per quarter. So if I do one switching per quarter, the wave will be like this. At some angle alpha, I did one switching per quarter. This is my output voltage. I did one switching per quarter. Now, after 1 quarter, how to complete that wave? After 1 quarter, how to complete that wave? You complete the wave such that the wave remain odd, because previously it was odd, no? It was odd signal. So it should remain odd, plus it should contain odd half wave symmetry. It should contain odd half wave symmetry. It should contain odd half wave symmetry. Odd half wave symmetry. It should contain odd half wave symmetry. Let me repeat this again. What you need to do is you need to do this one switching per quarter. It means in 1 quarter up to pi by 2. Pi by 2 is called 1 quarter. Up to pi by 2, you need to do one switching. If you do one switching like this at alpha, we call it 1 quarter switching. One switching per quarter. Now after pi by 2, how to complete this wave? After pi by 2, you have to complete the wave such that the wave should be odd and it should contain odd half wave symmetry. Now how to complete that? It's very simple. After pi by 2, what you need to do is, such that the symmetry remains same, such that this symmetry remains same, what you need to do is you just make the mirror image about this line, about this pi by 2 line. You make the mirror image. So if I make the mirror image, this line of mirror image of this line, if you look at this will be like this, okay, up to pi. This is my pi point. So up to pi, you can see that this side and this side is same. Up to pi, don't look at further, from pi onwards. Up to pi, you just see. If you look at up to pi instant, then you can see that at pi by 2, it is mirror image. Now at pi, what should I do? At pi, whatever this wave is, you just invert it. I mean, this positive side will come to negative side here. And this positive side, this negative side will go to positive side here. So this way you can invert the wave. Now, if you do like this, then the signal will remain odd and odd half wave symmetry will also be there. If the signal is odd and contain odd half wave symmetry, then we call it quarter wave symmetry. So you can say that the signal is quarter wave symmetric. We call it quarter wave symmetry. Okay, then the signal will be quarter wave symmetric. Okay. If the signal is odd and contain odd half wave symmetry, then we call it quarter wave symmetry. Now, what is the advantage of doing the switching like this? Because previously we have done the switching like this, 0 to pi by 2, 0 to pi, SA plus and SB minus were on, and from pi to 2 pi, SB plus and SA minus were on. So we have done the switching like this. Now I change the method. The method is in 1 quarter I do one switching. And then after pi by 2, the switching should be such that the wave should contain odd half wave symmetry and the signal itself should be odd, so that quarter wave symmetry remains in the wave. Okay. So now I did one switching per quarter. What is the advantage of this? Now the advantage is, let's calculate the fundamental third and the fifth harmonic in this. Let's see what is the fundamental component here, what is the third harmonic component here, and what is the fifth harmonic component there. So let's try to calculate it and let's see what is the advantage of doing the switching like this. So if you look at the fundamental component, let's first calculate the fundamental component. So the fundamental component will be, if you look at the fundamental component, then the fundamental component using quarter wave symmetry. If you know the quarter wave symmetry method, then you can easily calculate the fundamental component. Since the wave has quarter wave symmetry, and I need to calculate the amplitude of fundamental component. The amplitude of fundamental component. So how to do the how to calculate the fundamental component amplitude? V01 peak value will be equal to, using quarter wave symmetry, I am applying the Fourier analysis. I am applying the Fourier series method. So 4 by pi, I need to integrate from 0 to pi by 2, whatever signal ft is or vt is, into sine of omega naught t d omega naught t. This will give you the peak value of the fundamental component. Now ft is this. This is my output voltage under 1 quarter. I have to look under 1 quarter because the signal is quarter wave symmetric. That's why I'm interested in under 1 quarter only. So you can see that if you calculate this value, it will be 4 by pi. Now you can see that from 0 to alpha, the function value is VDC, FT is VDC. FT is VDC into sine of omega naught t, d omega naught t. And from alpha to pi by 2, the function is minus VDC into sine of omega naught t, d omega naught t. Okay. This will give you the amplitude, the peak value of the fundamental component. Now let's try to calculate this. So V01 peak value will be equal to, take this VDC out now. So it will become 4 VDC upon pi. 4 VDC upon pi. Now, if you integrate this sine of omega naught t, integration of sine of omega naught t will be minus cos omega naught t, upper limit minus lower limit. If you do like this, you will get 1 minus cos of alpha. Okay, this will be my upper limit minus lower limit. Similarly, you have minus sine omega naught t here. And if you integrate minus sine omega naught t, you'll get cos omega naught t. And if you do upper limit will be 0 minus lower limit, you'll get double of it. You get double of it here. Okay. So this will be the amplitude of the fundamental component. Now, how to calculate the amplitude of third harmonic? The amplitude of the third harmonic will be again 4 by pi, 0 to pi by 2, under 1/4 again I have to solve because the signal contains quarter wave symmetry. If the signal has quarter wave symmetry, then again I have to solve it under 1/4 only. So 4 by pi, 0 to pi by 2, FT. What is FT? Let's put FT here. FT into sine of 3 omega naught t, d omega naught t, because we are interested in calculating peak value of the third harmonic component. So in third harmonic component, just replace this sine omega naught t with sine 3 omega naught t. Okay, sine 3 omega naught t, and you can calculate the third harmonic amplitude. So the third harmonic amplitude will be 4 VDC upon 3 pi 1 minus 2 cos of 3 alpha. Okay, this will be the amplitude of third harmonic. You can check it. Okay. Excuse me. So I told you what is the amplitude of third harmonic. So this way you can calculate the amplitude of fundamental and the third harmonic component. Amplitude of third harmonic component can be calculated. Similarly, you can calculate the amplitude of fifth harmonic. The amplitude of fifth harmonic will be 4 VDC upon 5 pi 1 minus 2 cos of 5 alpha. Now, what is the advantage of switching this? Now, what is the advantage of doing like this? One switching per quarter. Why I have done like this? Because look at the fundamental and the third and the fifth. If you want to eliminate this third harmonic, what you need to do is you make it equal to 0. You'll get the value of alpha. At that alpha, you do the switching. Okay? And the third harmonic will not be there in the output voltage. In the output voltage, third harmonic will not be there. Third harmonic will be absent. So this is a good idea. This is a good idea. Okay? Let's say you want to eliminate the third harmonic. So make it equal to 0. If you make it equal to 0, then this term should be 0. It means cos 3 alpha should be 1 by 2. It means 3 alpha should be 60. 3 alpha should be 60. So it will become cos 60. Cos 60 is half. Half into 2. It will become 1 minus 1. 1 minus 1 is 0, you can say. So now you can say that if 3 alpha is 60 degree, then the third harmonic will be eliminated. And if 3 alpha is 60 degree, what is the value of alpha? Alpha must be 20 degree. Okay, this alpha came out to be 20 degree. I hope you understood it. Okay, so remember this point. This way we can eliminate the third harmonic. We can eliminate the third harmonic. Similarly, we can eliminate fifth harmonic. If you don't want to eliminate third harmonic, let's say, you can eliminate fifth harmonic. Okay, it's your choice which harmonic you want to eliminate. But there is a problem with this method. In one switching per quarter, there is a problem. The problem is, let's say you want to eliminate third harmonic. To eliminate third harmonic, you have fixed alpha equal to 20 degree. You have put alpha equal to 20 degree. Let's say at alpha equal to 20 degree, third harmonic is eliminated. But that alpha will decide the peak value of fundamental. It means the fundamental will also be affected by that alpha. If you fix that alpha to eliminate the third harmonic, that alpha will be fixed, and that alpha, I should put it here. So that alpha itself will dictate the amplitude of the fundamental. This we don't want. This we don't want, because we want to control this fundamental separately and this third harmonic separately. I don't want that if you select that particular alpha to eliminate this third harmonic, let's say alpha is 20 degree, that alpha will decide all the other harmonics amplitude. I don't want to do that like that. So what you need to, what we need to do to overcome this situation, to overcome this problem, to eliminate this situation, to eliminate this problem, there is one method: increase the switching per quarter. So now what I want to do is, I want to increase the switching per quarter. Now look at this. Today my health is not with me, so sorry from my side, guys. Anyway, look, this is my pi by 2, 1 quarter. What I did is, I did two switching per quarter. I did 2 switching per quarter. If you do 2 switching per quarter, then the output voltage will look like this. Output voltage will look like this. This is alpha 1 and this is alpha 2. This is VDC by 2. This is VDC and this is minus VDC. Because I am looking the output voltage, V not T. I'm looking the output voltage. Okay. So now I did 2 switching per quarter. And remember, after pi by 2, how to plot this, how to complete this wave? I have to complete this wave such that odd and odd half wave symmetry. Signal should remain odd and there should be odd half wave symmetry. These symmetries should be there in the wave. So if you want to complete this wave, how to complete that? It's very easy to complete, such that the symmetry, the quarter wave symmetry remains in the wave. What you can do is, you can take the mirror image of this signal. So first, you plot the mirror image like this. You plot the mirror image like this. Okay? Up to pi. This is pi point. Okay? This is up to pi point. Now, after pi, you just invert it. Whatever you have positive here, you have to take negative at this point. I mean, you have to invert this complete. Whatever this wave is, this starting point should be negative here. Okay? Invert it here. Via this way, the signal will contain the quarter wave symmetry again. Okay, so I want to do like this. So, but I am not interested in this part, because I know that I have to maintain the symmetry. So don't look at this. Just assume that by default I have maintained the symmetry conditions. So up to 1 quarter, if you look at the 1 quarter period, under 1 quarter, I have maintained the quarter wave symmetry. Okay. Now I need to calculate the fundamental peak of the fundamental component. So if you try to calculate the peak value of the fundamental, it will be equal to 4 VDC upon pi 1 minus 2 cos of alpha 1 plus 2 cos of alpha 2. This will be the amplitude of the fundamental component. Now, how to calculate this? It's very simple. I told you the peak value of the fundamental component can be calculated as 4 by pi from 0 to pi by 2. Whatever this signal V naught T is, you just put the value, and since the signal is odd, that's why I have to take sine of omega naught T, because I want to calculate the fundamental. If you want to calculate the third harmonic amplitude, then you have to take sine 3 omega naught here. Why I have taken sine? Because the signal is odd and the odd signal contain only the sine terms. If the signal were even, then I have to take cosine terms here. This way you can apply the quarter wave symmetry. Now if you open it, you will get 4 by pi from 0 to alpha 1. From 0 to alpha 1, amplitude is VDC. VDC sine of omega naught T, d omega naught T, plus from alpha 1 to alpha 2, from alpha 1 to alpha 2, it's minus VDC into sine of omega naught t d omega naught t plus from alpha 2 to pi by 2. From alpha 2 to pi by 2, it's VDC sine of omega naught t d omega naught t. Okay. So this way we can write like this. This is the peak value of the fundamental component. Take this VDC out. If you take this VDC out, you will get 4 VDC upon pi. 4 VDC upon pi. Here in this integration, I have sine of omega naught t. If it integrate it, you will get minus cos of omega naught t. Upper limit minus lower limit, you will get 1 minus cos of alpha 1. Okay. Similarly here, you have minus sine of omega naught t. If you integrate it, you will get cos of omega naught t. Take upper limit minus lower limit. So if you take lower limit, it will be doubled. And upper limit, you will get cos alpha 2. Similarly here, you have sine omega naught t. You take the integration, it will become minus cos omega naught t. Put the upper limit, it will be 0. Minus lower limit, it will be doubled here. Okay. So this will be my output voltage now. This is the peak value of the output voltage, fundamental. Now let's come to the third harmonic. So in third harmonic, what you need to do is, in place of sine omega naught t, you just put sine 3 omega naught t. Okay, and you can calculate the peak value of the third harmonic component. So the third harmonic component peak value will be 4 VDC upon 3 pi 1 minus 2 cos 3 alpha 1 plus 2 cos 3 alpha 2. This way you can calculate the amplitude of third harmonic. Similarly, you can calculate the amplitude of fifth harmonic and seventh harmonic. Obviously, it contains odd half wave, no? It contains odd harmonics only. Here, in place of 3, you have to write 5 because you are writing fifth harmonic. Okay, so it will be 1 minus 2 cos of 5 alpha 1 plus 2 cos of 5 alpha 2. Okay, this will be my fifth harmonic. And there will be more like 7th and 9th. So those harmonic will also be there. Now, using these two switching per quarter, what I can do is, now I can control the amplitude of the fundamental and I can eliminate the third harmonic. Let's say I want the amplitude of the fundamental equal to, maybe let's say you want the peak value of the fundamental equal to half of VDC. And you want to eliminate the third harmonic. So you can put it equal to 0 and you can put it equal to VDC by 2. Now you have two unknown, alpha 1 and alpha 2. You can calculate the corresponding alpha 1 and alpha 2. Now it's easy to control one amplitude, one harmonic amplitude you can control and one harmonic you can eliminate, because now you have two control. You have two variable, alpha 1 and alpha 2. Using this concept, what you can do is you can control the amplitude of one harmonic. Let's say you want to control the amplitude of the fundamental. Okay, so you can take it like whatever you want. Let's say it's VDC by 2 you want. So the amplitude of the fundamental you want VDC by 2. And let's say you want to eliminate the third harmonic. So you can do like this. Okay. Now, if you want to eliminate the harmonics only, let's say you want to make third harmonic equal to 0 and fifth harmonic equal to 0. Okay. Let me tell you one more thing. Let's say you want to eliminate the third harmonic and fifth harmonic. You can do it. Accordingly, you can calculate alpha 1 and alpha 2. Now, if you get to alpha 1 and alpha 2, then that alpha 1 and alpha 2 will dictate this fundamental. It means now you can't control this fundamental amplitude. Now you can't control this fundamental amplitude. Okay, this is the problem here. If you make it 0, the third harmonic 0 and the fifth harmonic 0, then the problem is you'll get alpha 1 and alpha 2 from these two equations. But the problem is you can't use that alpha 1 and alpha 2 to control this. No sir, alpha 1 and alpha 2 are fixed. If alpha 1 and alpha 2 are fixed, then this will also be fixed. So now you have two control. Either you eliminate two harmonics or you eliminate one harmonic and control fundamental, or you don't control the fundamental and you can eliminate the two harmonics. Now it means only two choices is there. How to increase the choice? How to increase the choice? Tell me guys. It's simple. If you want to eliminate two harmonics, let's say, and if you want to control this also, then you should have three variables, alpha 1, alpha 2 and alpha 3. It means you have to increase the switching per quarter. Now you have to take 3 switching per quarter if you want to eliminate 2 harmonics, and again you want to control the fundamental amplitude. So you want 3 pulses. You want 3 pulses per quarter cycle. Okay. So again you can increase and you can calculate that alpha 1 and alpha 2 correspondingly. I mean, whatever you want. Let's say you want to eliminate this and you want to control this. So you have to take 3 switching per quarter. If you want to eliminate 3 harmonics and you want to control the fundamental, then you need to do 4 switching per quarter. Okay. Let's say you do 3 switching per quarter. Let's take 3 switching per quarter. In 1 quarter, if you take 3 switching, this is my pi by 2. And what you do is, under 1 quarter, you take 3 switching. Alpha 1, alpha 2, and let's say alpha 3. Okay. This is alpha 1, this is alpha 2, this is alpha 3. Now here, if you want to calculate the fundamental component, let's say this is VDC, output voltage VDC, and this is minus VDC. If you calculate the peak value of the fundamental, it will be 4 VDC upon pi 1 minus 2 cos alpha 1 plus 2 cos alpha 2 minus 2 cos alpha 3. This will be the peak value of the fundamental. The peak value of the third harmonic will be 4 VDC upon 3 pi 1 minus 2 cos of 3 alpha 1 plus 2 cos of 3 alpha 2 minus 2 cos of 3 alpha 3. Okay. This is the peak value of the third harmonic. Similarly, you can calculate the peak value of the fifth harmonic. 4 VDC upon 5 pi 1 minus 2 cos 5 alpha 1 plus 2 cos 5 alpha 2 minus 2 cos 5 alpha 3. It's very simple. Now let's say, now you have 3 variables. So there should be 3 equations to calculate this alpha 1, alpha 2, alpha 3. Now what you can do is you can eliminate these 2 harmonics. Let's say you want to take third and fifth equal to 0 and you want to control the fundamental. So whatever value you want to take, let's say VDC upon 2. You want to take this fundamental amplitude to be VDC by 2 and you want to eliminate third and fifth. Now you can do it because you have 3 variables. You have 3 variables. So it's easy to calculate now. But it's not easy to calculate because you can't calculate alpha 1, alpha 2, alpha 3 by using, I mean, you can't do the calculation. You have to apply some Newton-Raphson method or some numerical methods you need to apply. Okay. But there is a way to calculate alpha 1, alpha 2, alpha 3. If you further increase the switching per quarter, if you increase the switching per quarter, then there is more control in your hand. There is more control in your hand. Okay, so everything is switching game. If you do the switching of these SA plus and SB minus, SA plus and SB plus and SB minus, if you do the switching such that under 1 quarter there is many switching. In 1 quarter, let's say there are 20 switching. Obviously, you can control more and you can eliminate more harmonics by taking alpha 1, alpha 2, alpha 3 appropriately. Okay. So you can appropriately select these alpha 1, alpha 2 and alpha 3. If you can select this alpha 1, alpha 2, alpha 3, then you can eliminate the harmonics. Even higher harmonics you can eliminate if you can increase the switching per quarter. Okay. I think it's easy to understand. But the problem is, it's very difficult to calculate this alpha 1, alpha 2, alpha 3, alpha 4, alpha 5 and things like this. Okay. So it's very difficult. So we want a method in which we don't need to find this alpha 1, alpha 2, alpha 3. Automatically, they should be adjusted such that the lower harmonics should not be there in the output voltage. They automatically will be eliminated. We want this type of method. If you want this type of method, then there is a sinusoidal PWM. Then the method is sinusoidal PWM. Okay. In sinusoidal PWM, what we need to do is we have 2 types of switching. We have 2 types of sinusoidal PWM. That is bipolar PWM and one more is unipolar PWM. Okay. One is bipolar PWM and unipolar. Here you don't need to think about what is the switching instant. Okay. What is alpha 1 and what is alpha 2. You don't need to calculate that. Okay, the way will automatically handle that. Now, how to handle that and how this switching takes place? So let's try to understand sinusoidal PWM with bipolar PWM. Now, what is the bipolar and unipolar? First of all, we will try to understand the bipolar PWM. In bipolar PWM, we will make a group of these two, like SA plus and SB minus. In bipolar PWM, SA plus and SB minus, they are under one group. They will turn on and turn off at the same instant. It means they are under one group. Similarly, SA minus and SB plus are under one group. They will turn on and turn off at the same instant. And remember, there is one more point. You can't turn on SA plus and SA minus simultaneously. If SA plus is on, then SA minus has to be turned off. Okay, you can't turn it on, otherwise the source will be sorted. Okay, so remember this point. In bipolar PWM, we have a group of switches like this. There is one group of SA plus and SB minus, and there is one more group of SB plus and SA minus. So you have to do the switching like this, otherwise it's difficult. In bipolar, leg A and leg B are connected. The switching should be like this only. Now in unipolar, if you look at the unipolar, in unipolar we don't have this grouping. We can switch on and off this leg separately and this leg separately. Okay, we don't want to make the grouping. Okay, we'll operate this leg separately, we'll operate this leg separately in unipolar PWM. Okay, so there is no grouping in unipolar PWM. One more important point is whether the PWM is unipolar or bipolar. Remember this point, that you are not going to switch on both the switches at the same instant. Let's say in leg A. In leg A, if SA plus is on, then SA minus has to be off. You can't turn on both the switches, or you can't turn off both the switches. Okay, either this should be on or this should be off, or this should be on, this should be off. Okay, so simultaneously in each leg, this A leg and in B leg, in each leg simultaneously two switches should not be either turn on and turn off. Turn off is possible when two switches can be turned off at the same instant. There is no problem. That is called blinking period. But they cannot be turned on at the same instant because they will sort the source. So remember. Now let's come to bipolar PWM. Now how to do the bipolar PWM? To understand the bipolar PWM, what I need to do is I need to make a triangular wave. This is the triangular wave, guys, and let me remove this because there is a typing mistake here. So let me remove this. This triangle is not there. The typist made the triangle. Let me correct this. Okay. So in bipolar PWM, we have a triangular wave and we have a sinusoidal wave. Wait a minute, guys. Okay. Let's remove this again. So we have a triangular wave like this. I am removing this extra because there is a typing mistake here and the typist did this mistake anyway. Similarly, let's remove this part. Remove this part also because this is not required. In bipolar PWM, we don't require this. Okay. That's why I am going to remove it. This side also you can remove it. Okay. So now you can see that Okay, I think it's enough because it's wasting my time. Anyway, so there is a triangular wave. There is a triangular wave. You can see that. There is a triangular wave. This is the triangular wave we have. And there is a sinusoidal wave we have. There is a sinusoidal wave. Now, if you can see, this we call V control. V control. This sinusoidal we call V control. And this wave we call V triangular. V triangular. Okay. V triangular. This wave is called V triangular. We call it V control. The control signal, and moreover, this wave is wrong actually, because if you see carefully, you have in this first positive half, you have covered three triangles, three period of this triangular wave, and here you have only covered two triangles. So actually there is a typing mistake. Okay, but anyway, you'll understand, don't worry. So what I can do is, this is my V triangular and this is my V control. Whenever this V control is greater than, whenever V control is greater than V triangular, whenever this V control is greater than V triangular, then what I need to do is, I need to turn on SA plus and SB minus. Then I need to turn on SA plus and SB minus should be turned on, and they should remain turned off, because I am using bipolar. So in bipolar PWM, what I need to do is, I need to make the grouping. So whenever this V control is whenever this V control is greater than V triangular, then SA plus and SB minus should be turned on. And whenever this V triangular is greater than V control, then SB plus and SA minus will be on. I hope you understood it. Now you'll ask me, sir, what is the advantage of this? The advantage is, look at the output voltage there. Okay, let me plot the wave again. First of all, let me plot the triangular wave. Let's say this is the triangular wave I have. Let's say this is the triangular wave I have. Let's do it further. This is the triangular wave. Now I want the V control signal. So V control signal should be, let's say this is 1 period, 2 period, 3 period, 4, 5, 6, 7. Let's take it here. So, wait a minute, guys. Yes. So this point is at 7th period, no? So I take the V control like this: 1, 2, 3, 4, 5. Let's draw one more. Yeah. So now 1 period, 2, 3, 4, 5, 6, and 7. So here I have to complete the second half. Okay, so this is my V control. This is V control, this is V triangular. Whenever this triangular is high, whenever this V control is high, okay, now in this interval, if you look at this interval from this point to this point, if you look carefully, V control is higher than V triangular. So you can say that SA plus and SB minus will be on, then the output voltage will be plus VDC. So the output voltage will be plus VDC during this interval. And then from this point to this point, V control is less than V triangular. So you can say that opposite switches are connected. If you turn on opposite switches, then the output voltage will be minus VDC. Okay. During this interval to this interval, it's minus VDC. And then again, you'll have from this point to this point, V control is greater than V triangular. It's plus VDC. Okay, it's plus VDC. Is it fine? It's plus VDC. From this point to this point, it's plus VDC. And then from this point to this point, output voltage is minus VDC. Okay, it's minus VDC. And then from this point to this point, again plus VDC, and then again minus VDC for the small interval. I hope you understood it, how the voltage will look like. Similarly, from this point onwards, let me plot for some first half. Again, it will be like this, and then go like this. This will be my output voltage, guys. Now, in this output voltage, the lower harmonics will not be there. The lower harmonics will not be there. Okay, so this will be the wave. Now you can see that the positive area is greater than the negative area. Up to this point, the positive area will remain greater than the negative area. Okay, the positive area will be greater than the negative area. Okay, after in the next half, if you look at the next half, in the next half, the negative area will be greater than the positive area, because you can say that in this interval, the V control is V triangular is greater than V control. So you can say the output voltage will be minus. So this more area will be of negative. Negative area will be more than the positive area. Here the positive pulses has the more area than the negative pulses. But in the second half, the negative pulses will have the more area than the positive pulse. So you can say that the output voltage will not contain the DC component. The average value under one period. If you look at this period up to this point, this we call one period. Up to one period, whatever the positive area is, the same is the negative area. Because 0 to pi, if you look at the area, then the area will be positive, because the positive pulses are more than the negative pulses. I mean, the area of the positive pulse is more than the negative area. So you can say that the positive pulse area in one half period, positive area is there, and in next half period, negative area will be there. So under one period, the total area will be 0. So there is no average voltage. There is no average voltage in the output voltage. Okay, in output voltage, in V naught T, you don't have the average value. Okay, in output voltage, you don't have the average value. Now, some points you need to remember. This V control, you have to take the frequency of this control signal to be equal to the fundamental frequency you want. Let's say you want 50 Hertz. Okay, you want the fundamental component to be of 50 Hertz. Then what you need to do is, you need to take this V control signal of 50 Hertz. The frequency of this V control signal should be equal to the frequency of the fundamental component. Okay, the frequency of the fundamental component you want. I hope you understood it. So this way you can do the switching like this. Now, what is the advantage of this? The advantage is, in this case, you don't have lower harmonics. You have higher harmonics. Now, what are those higher harmonics? What are those higher harmonics? How to calculate what are those higher harmonics? To calculate higher harmonic, you need to calculate the frequency modulation index. Frequency modulation index. Now, what is this frequency modulation index? What is this frequency modulation index? We call it MF. MF is frequency of triangular wave. Frequency of triangular wave divided by the frequency of control signal. Control signal. This will be my MF. Okay. Now, look, in one half period, how many triangles are there? 1, 2, 3, 4, 5, 6, 7. So you can see that in one half period, you have 7 triangular waves. You have 7 triangular waves. In one half period, you have 7 triangular waves. In one half period of this control signal. So in complete period, if you look at the complete period, in complete period of this control signal, you have 14 triangular waves. You have 14 periods of the triangular wave. It means you can say that this ratio came out to be 14. Okay, this modulation index, frequency modulation index, we call it 14. And there is one more term, we call it amplitude modulation index, MA. We call it MA. Now what is this MA? What is the amplitude modulation index? Amplitude modulation index can be calculated by using this ratio. Wait a minute, guys. Okay, so now I want to calculate the amplitude modulation index. Now in case of amplitude modulation index, what I need to do is I need to look at the amplitude of the control signal, and I need to look at the amplitude of the triangular signal. That ratio, peak value, look at the peak value of the control signal and the peak value of the triangular signal. This is the peak value of the control signal and this is the peak value of the triangular signal. You take this ratio, you call it amplitude modulation index, MA. We call it amplitude modulation index, MA. MA is V control peak value divided by V triangular peak value. This ratio we call MA, modulation index, amplitude modulation index. Okay, this way you can calculate the amplitude modulation index. And this is the frequency modulation. Frequency modulation index will tell us about the order of harmonics. The order of harmonics. It means the order of the harmonics will be 14 times of, the fundamental is there, and then third, fifth, seventh, these harmonics will not be there. Now the next harmonic will be multiple of 14. Like 14 into, let's say 14 into 2 plus minus 1. Okay, because odd harmonics are there. Na? So the next harmonic will be 27th or 25th or maybe 29th. Okay, so this way you can calculate the harmonics, the amplitude of the, the next harmonic will be, harmonic frequency will be multiple of, integer multiple of this plus minus 1. You have to make it odd, na? You have to make it odd because odd harmonics will be there. Is it fine? So this way you can calculate, you can see that the lower order harmonics will be eliminated. You will have the higher order harmonic. But higher order harmonic can be filtered out easily. Because to eliminate higher order harmonic, you can have L and C, and the magnitude of L and C required is not that much high. So you can say that the amplitude of L and C can be minimized using this sinusoidal PWM. Now, what is the fundamental? What is the amplitude of the fundamental component? What is the amplitude of the fundamental component using PWM sine wave? Sinusoidal PWM. What is the amplitude of the fundamental component in the output voltage? In this output voltage, you have the fundamental term, and we are interested in calculating the amplitude of the fundamental wave. So the amplitude of the fundamental wave will be MA into VDC. MA into VDC. This will be the amplitude of the fundamental. Amplitude now, tell me. I think the video is gone. Okay. Now it's visible. Okay, thank you. So I told you how to calculate the amplitude of the fundamental. The amplitude of the fundamental is MA into VDC. This MA. MA is the modulation index. This MA into this output voltage VDC. Now how we have calculated this? It's not important for now. Okay, because the time is over, and I will cover this this topic in some other session, but I hope you understood how to do the sinusoidal PWM and why to do the sinusoidal PWM. Because in sinusoidal PWM, the good thing is the switching. We have to calculate this alpha 1, alpha 2, alpha 3, alpha 4 to eliminate the harmonics. Now it's not necessary to calculate this alpha 1, alpha 2. Automatically it will handle. How it will handle? You just compare the control signal with the triangular signal. Wherever the triangular signal is more than the control signal, then these two switches will be on. Whenever this V control is higher than the triangular, then these two switches will be on. Okay, and this way what you can do is you can do the switching like this. I mean, this SA plus and SB minus should be on such that the output voltage is like this. Okay, and you don't need to calculate this alpha 1, alpha 2, alpha 3, alpha 4. No sir, it's not required. Okay, it will automatically handle the situation. Okay, it will automatically eliminate the lower order harmonics and you will get the higher order harmonics, and the amplitude of the fundamental component will be MA into VDC. Okay, now how we have achieved this, how we got this point, we'll discuss in some other session. In unipolar PWM, what we have is, in unipolar PWM, we have leg A and leg B. For leg A, we have this control signal. This is the control signal for leg A. Okay, I mean, the formula will remain same. This is V control. Wait a minute. Yes, this is V control A. This is V control A. It means this is the control signal for leg A. And this is V control for leg B. V control for leg B. V control for leg B. Okay. So this is the V control for leg B. And again, there is a typing mistake, because you can see that here you have in this first half, there are more triangular periods than in the second half. So it's a mistake done by the typist. Anyway, this cycle should be same as this cycle. No? I mean, the triangular period. If you look at the triangular period in this half control signal, then 1, 2, and I mean, it's not correct. Okay, that's why. Anyway, whenever V control is greater than the V triangular, then SA plus will be on. So in this unipolar PWM, we will separately use PWM for this leg and this leg. We have not made the grouping. Okay, SA plus and SP minus are not grouped. Similarly, SB plus and SA minus will not be grouped. Okay, so separately we will operate SA plus and SA minus. Similarly, SB plus and SB minus separately we will operate them. How to operate them? Look at this leg A. In leg A, whenever this V control is greater than V triangular, then SA plus will be on. Otherwise, SA plus will be on. SA minus will be on. Okay, is it fine? So let me repeat this again. I told you, whenever in leg A, whenever this V control of A is greater than V triangular, then SA plus will be on, otherwise SA minus will be on. So here the voltage will be, if you look at the voltage at this point, the voltage will look like this. If SA plus is on, let's say during this point to this point, this V control A is greater than this V triangular, so you can say that it will be positive. And then from this interval to this interval, you can say that SA minus is on, because V triangular is greater than V control. So this point voltage will be 0. Okay. And then again, from this point to this point, again you have positive voltage. Now you can see that here at this point, the voltage will be positive, will not go negative. That's why we call it unipolar. But in previous case, since we have made the grouping, and we are looking at the output voltage, and the output voltage has the positive pulse as well as the negative pulse. So that's why in the previous case we call it bipolar. But in this case, at this point you have the positive voltage, and at this point you have the negative voltage. Let me show you. This is VAO and this is VBO. If you plot VBO, then you have to look at the V control of leg B. whenever this V control is greater than whenever this V control of leg B is greater than the triangular wave, then SA plus is on, and whenever it is less than the triangular wave, then SB minus will be on. So similarly, you can plot the wave at output voltage at B point, okay, and the voltage at B point will be like this. Let me tell you, from this point to this point, since V control is greater than this triangular, so you can say that the output voltage will be plus VDC during this interval, and then from this point to this point, output voltage will be 0, and then again the V control is greater than, then the output voltage will be like this. Okay, so I mean you can plot the VB also, and if you take the difference, then the output voltage will look like this. Let me plot the output voltage. The output voltage will be like this. The output voltage will look like this. Okay, this will be my output voltage. So you can see that in the output voltage from 0 to pi you have only positive side, and from pi to 2 pi you have only the negative side. If you take the difference now, VAO minus VBO, you'll get this point, you will get this type of wave. We call it unipolar. Why we call unipolar? Because we have only positive side or negative side. We don't have both side in output voltage, because previously you have positive as well as negative, no? But here we don't have the negative side in positive in 0 to pi, and then pi to 2 pi you have negative side always. Okay, so we call it unipolar. Again, the fundamental amplitude is MA into VDC. The peak value of the fundamental is MA into VDC. It will remain same. The peak value of the fundamental will remain same. Why it is MA into VDC, we will discuss in some other session, or I'll complete this PWM and how for VAO and VBO, how I have plotted. I'll take it in some other session on PWM. Okay, so I hope you enjoyed this session. I hope you understood why we go with sinusoidal PWM and what is the amplitude of the fundamental component of the output voltage. So I hope you understood it. So in some other session we will discuss about this unipolar and bipolar, because mainly the unipolar I need to cover, and I need to tell you why this MA into VDC is there. Okay, so why how this MA into VDC came into picture. So I'll discuss this in some other session. I hope you enjoyed. So that's all for today's session, guys. See you in the next session. My next session will be on synchronous machine, and I will take some questions on synchronous machine. Okay, so that's all for today's session, guys, and see you on tomorrow. Tomorrow I have a session on synchronous machine, questions on synchronous machine. I hope you will like them also. Okay, so take care, and thank you for showing interest in this class. Bye.